Thank you. Let me first start by thanking the organizers for organizing this very nice workshop and for having me here today. I am going to tell you about graphene-based magnetic heterostructures and the fact that in our research we are trying to modify or manipulate the spin-related properties of graphene in order to have it more suitable for spintronic devices. And in particular, today I would like to also highlight the presence of quantum spin-polarized edge states in these heterostructures, which allow for quantum coherent propagations of the spins at the edges of our channel, which is making these heterostructures quite promising for quantum spintronic circuitries. The motivation behind this research actually goes back to a decade of experimental research that is done in graphene-based spintronic devices, which is mainly explored in devices with such conventional geometry, where cobalt electrodes are used for the purpose of spin injection and detection. And graphene there in between is actually allowing for the spin transport from point A to point B. And graphene actually does an excellent job here because it has high charge carrier mobility and low spin orbit coupling, which allows for long distance spin transport and not much of spin dephasing. However, graphene by itself doesn't have much of spin-related functionality, because if you look at the band structure, it's actually missing any form of spin polarization. So if you want to have that, you would have to actually induce either spin orbit coupling or exchange interaction, and that can create some form of spin polarization in the graphene band structure. But how do we do that? Well, proximity effect tells us that if you bring graphene in the close proximity of various two-dimensional materials, there can actually be an overlap between their electronic wave function, which would allow for combining their properties. So as a result, if you bring graphene in the close proximity of 2D magnetic materials, which are actually made of heavy elements, so they are like supposed to have strong spin orbit coupling, and also they are magnetic, so they are expected to have strong exchange interaction, then by their proximity you can actually induce both in graphene, and as a result you will have such spin polarized band structure. And as a result of that, there are like various effects emerging, such as spin-dependent conductivity, spin-dependent Seebeck effect, anomalous Hall effect, and possibly quantum anomalous Hall effect. And these are the effects that I would like to walk you through with me today. The first experiment that we did was with chromium sulfur bromide. Well, you're already well familiar with this material. It's an interlayer antiferromagnet with a magnetization within the plane, and then the moment that you bring your graphene on top, well, here we are using bilayer graphene, but that doesn't really matter. When graphene comes on top, it actually senses the magnetization of this outermost layer of the CSP, which is going to get induced in graphene, and that can create a spin polarization in the band structure. Looking at what is happening at the Fermi energy, you actually realize that the density of the spins for spin up and spin down electrons is not the same. The carriers with higher density are going to have higher conductivity, so your magnetized graphene should have a finite spin polarization of conductivity. And this you can actually directly measure using spin-sensitive cobalt electrodes. And for that, we are actually using this rather conventional three-terminal measurement geometry. The resistance that you would measure here, this three-terminal resistance, is the interfacial resistance that is present there at this central contact. So by measuring that, you will measure the interfacial resistance that you're having in between cobalt and graphene. And now you can apply an external magnetic field and play with the relative orientation of the magnetization of cobalt with respect to magnetization of CSP. So you can actually go from parallel configuration to anti-parallel configuration and back to parallel again. And you see a clear spin-related switches that is happening here. And the magnitude of this switch is directly proportional to the spin polarization of conductivity in graphene. And from there, you can actually extract it to be about 14%. This is actually quite large. It's actually comparable with that of cobalt contacts, as you see. And that implies that when graphene becomes magnetized, it can actually also participate in the process of spin injection and detection rather efficiently as it is compared with cobalt contacts. So magnetized graphene seems to be able to actually replace the cobalt contacts for the purpose of spin injection. And this is something that we also show in practice in this other work, where we are replacing our cobalt electrodes with normal electrodes. And in this part of the circuit, wherever the current is passing through the magnetized graphene region is going to inject spins to the other parts. So graphene is the only spin injector in this circuit. And it's proving that indeed it can inject spins because we are again, seeing these spin-related switches. The other effect that I mentioned in advance is the spin-dependent Seebeck effect. This effect would be present in magnetized system where there is a thermal gradient. So here in our magnetized graphene channel, we have a thermal gradient which is generated by the Joule heating of the graphene channel at this current source contact. And then those thermally injected spins through spin-dependent Seebeck effect are going to actually diffuse in the channel and then get picked up by our cobalt detector contact. Because of the dependence of such thermal effects on current squared, you would have to take a look at the second harmonic of your signal, and this is what we do here. We are using AC lock-in technique, so we can dissociate it from the first harmonic measurements, and here again we are seeing spin-related switches telling us that when graphene becomes magnetized, it can not only inject spins electrically, but also thermally through spin-dependent Seebeck effect. Next effect that can pop up in such systems is the anomalous Hall effect, and this effect would be present in systems where there is both magnetism and spin-orbit coupling present. And if you want to pick this effect up in such geometry where the current is actually flowing along the channel and then you're picking up the transverse voltage, it would be very much dependent to the Z component of the magnetization. So initially, when the magnetization of the CSP is in the plane, there is no anomalous Hall effect, but as soon as you apply an external magnetic field and push the magnetization out of the plane, you are going to generate out-of-plane spin polarization. Now, these spins are going to have opposite trajectory because of the spin-orbit coupling. They are going to get accumulated at the edges of your channel. And since the system is magnetic, there is an imbalance in the number of these spins, and that would create a finite transverse voltage that you can pick up as your anomalous Hall signal. And this is exactly what we are measuring here, clear nonlinearity over Hall voltage, giving us quite a sizable anomalous Hall signal, which is also gate tunable, shrinking in size as we go further away from the charge neutrality point. Having observed this, which is a signature of the presence of both magnetism and spin-orbit coupling, we were actually curious if we can measure quantum anomalous Hall effect. It is actually theoretically predicted that if you have a strong enough magnetism and spin-orbit coupling, what will happen is that there will be a bulk gap opening in the graphene, and then within that gap there will be spin-polarized edge states present. So what you can do is to bring the Fermi energy within the bulk gap, and then that would allow for the realization of these spin-polarized edge states that are ballistically propagating at the edge of the channel. And the good thing about it is that for observation of this, you actually do not need the external magnetic field because the induced magnetism and spin-orbit coupling already can create such a situation that would allow for these quantum spin-polarized edge states. So without an external magnetic field, you can actually realize quantum anomalous Hall effect. For observation of this effect, we actually shifted to another 2D magnet. You also heard about this in the previous talks. So this is chromium phosphor sulfide that we are using. I call it CPS from now on. It's also an interlayer antiferromagnet, but with the magnetization mainly being out of the plane with slight canted situation. This is the top view of the crystal. If you cleave the crystal, it will get cleaved along the chromium atoms. And if you exfoliate the crystal, it will actually give you flakes with 67.5 degrees of corner angle. And then the bisector of your angle is your magnetic A-axis. So if you wish, you can actually align your graphene Hall bar as such that the graphene channel is along one of the magnetic axes. So here we are actually aligning it with the magnetic A-axis. Thank you. And now, the question is, how is the magnetic behavior of this material that you can actually check by discrete magnetometry? So initially, as I mentioned, we have this anti-ferromagnetic situation with slight canting, 20 degrees of canting with respect to the C-axis. Now you apply an external magnetic field, and the system undergoes the spin-flop transition. So the magnetization actually goes to the plane, as you see here. It's still keeping this anti-ferromagnetic alignment, but it goes to the plane. And then increasing the field further is going to actually create further canting of the magnetization, and that is the moment that you're actually generating a finite magnetization that you can pick up. And then increasing the field further is going to linearly increase the magnetization up to the saturation field that is happening around 8 Tesla. So there are like two ranges of the field that become important for us. One is when we are below 1 Tesla, where we are addressing the spin-flop transition. and one is what is happening above 8 Tesla, where we have the full saturation of the magnetization. And now the question is that whether we can see the reflection of this magnetic behavior in our graphene channel, which is placed on top. So first, I would like to show you what is happening in our transverse voltage measurement. Here we are measuring transverse voltage as a function of external out-of-plane magnetic field. In principle, this should give you the ordinary Hall effect, which is linear in field. But what we measure is slight nonlinearity over the Hall voltage together with switches that are happening around 1 Tesla. This is actually resembling the switches that we were having in the discrete magnetometry coming from spin-flop transition, right? How would we pick that up in our RXY measurement? Through anomalous Hall effect. Well, because the anomalous Hall effect is actually very sensitive to the Z component of the magnetization. So the moment that you went through the spin-flop transition, you actually created such slight canted situation, which is now picked up in our RXY measurement because the anomalous Hall effect is present. If you take a closer look at what is happening here, you actually see 2 switches. One is on the trace and the other one is on the retrace. How do we understand this? Well, you can imagine that even though graphene is like sensing the magnetization of the outermost layer, which is a ferromagnet, still the dynamics of this outermost layer is ruled by its anti-ferromagnetic coupling with respect to the bottom layer. So the outermost layer still undergoes spin-flop transition on the way forward and back. There is one more thing that I would like to actually highlight here, which is a surprise for us, and that is the magnitude of the anomalous Hall effect close to 0 is quite small. And this is a surprise because, as I mentioned, at 0 magnetic field, the magnetization is mainly out of the plane, but we are realizing that the signal here is quite small. And this means that probably the outermost layer is having a different canted situation compared with the bulk. And this is actually highlighting the fact that the magnetization of the outermost layer could actually have its own behavior in a way that is can differ from the bulk, and this is actually sort of highlights the beauty of these measurements because it's only sensitive to this outermost layer whilst it is interacting with the bottom layers. Now, what is the magnitude of the anomalous Hall signal? This is also interesting to take a look at. If you subtract trace from the retrace measurement, you actually can get the anomalous Hall signal, which is 80 ohm. And this 80 ohm is only coming from this switch. Slight canting of the magnetization, but still you have a very long way to go to bring the magnetization fully out of the plane. And now if you actually compare the magnitude of the magnetization at this point with what you have at the other point at 8 Tesla, you can simply extract the canted angle that you're having here, and that is giving us 6 degrees of canted situation. And that means that by 6 degrees only of the canted magnetization, we are generating 80 ohm of anomalous Hall signal. Now you can do the simple math and imagine what will happen if the magnetization gets fully out of the plane, and that would give you 700 ohm of anomalous Hall signal, which is quite sizable. And this is what we actually measure in practice. We bring the magnetic field up to 9 Tesla. We see that the anomalous Hall component reaches about 700 ohm. Well, there are extra wiggles here. That is because of the quantum Hall plateaus, because the system goes to the quantum Hall regime, which I will tell you in the next slides. But the signal starts from 700 ohm, but then by increasing the temperature, magnetization drops, and then your anomalous Hall signal also drops, but it is still persisting up to room temperature. So it seems like that we are still having a nonlinearity over our Hall voltage, creating anomalous Hall signal of about like 150 ohm, which tells us that the heterostructure is actually providing us with room temperature magnetism. Actually, in parallel with our work, there is also this other work published at similar time. There they have also seen this room temperature, Curie temperature in this particular heterostructure, which makes it quite interesting for applications. Now, I would like to bring your attention to the actual quantum transport that is happening in this heterostructure. So what I'm showing here is the longitudinal transport. Here we are measuring the resistivity picked up by this local 4-terminal voltage. Of course, what happens is that by applying a large enough magnetic field, you're creating Landau levels, right, as shown here. And then by gating, you're actually pushing the Fermi energy in between these Landau levels. Each time that the Fermi energy meets a Landau level, there will be a sudden increase in the density of states, and as a result, the resistivity increases. But then the moment that you're in between the Landau levels, you're addressing the edge states, and those edge states are basically ballistically propagating at the edge of your channel. These are the chiral states, creating zero resistance. And now, if we think about it, if we reduce the magnetic field, what will happen is that our Landau levels would get smaller. Of course, the Landau gap is dependent on the external magnetic field, and then these Shubnikov-Das oscillations are getting like closer to each other. And if you plot all this versus gate and versus magnetic field, you will have the so-called Landau fan diagram. Those who are familiar with quantum Hall transport in graphene already can tell that this Landau fan diagram is quite different from what is expected to be seen in pristine graphene. For example, the zeroth Landau level, you see that in pristine graphene, by increasing the field is expanding because of the like spin and valley splitting that is happening versus external magnetic field. Whereas here in our system, we are barely seeing much of broadening. That's one difference. The other thing is that we see that the Landau gaps are actually seem to be larger than the pristine graphene case. Actually, if you pick up the resistivity maximas versus gate voltage, you see that they are nicely linear, but then they are not meeting each other at the Dirac point. We are also plotting this here in the inset versus carrier density, and again we are seeing that these Landau fans are not meeting each other at 0 carrier density and 0 field, in contrast to the pristine graphene. Now you may wonder where this is coming from. That's a good question. Well, if you think about it, if the Landau levels are appearing at higher carrier density, that means that they are having higher energy, implying that the Landau gaps are actually larger. Larger Landau gap implies that the effective total magnetic field present in the system is actually larger than what you're applying. So here we are parameterizing that as B total, which is the field that you're applying plus a pseudo magnetic field present in the system. And now we can extract that for each Landau level. We see that we are applying 9 Tesla externally, but apparently the pseudo-magnetic field is creating a total field that can be as large as 15 Tesla. And again, the question is that where is this coming from? One thing is that you could have the dipolar stray field coming from the 2D magnet, but in a homogeneous substrate, that should be small. The other thing that we were thinking of is strain. Actually, we discussed that in the other talks. In particular, for the case of CPS, it is shown that it has a highly anisotropic mechanical response. So if you cool down CPS below 120 Kelvin, you actually realize that along A-axis it starts expanding and along B-axis is contracting. So the crystal undergoes quite a lot of strain, and now you have your graphene on top. So of course that graphene can also sense that strain gradient, and that can actually give rise to a pseudo-magnetic field, perhaps. Another signature of this pseudo-magnetic field actually becomes clear when you take a look at what is happening at the Dirac point at small magnetic field. This is what we see. We actually see that oscillations of the resistivity are persisting down to very small magnetic field. These oscillations of the resistivity are again our Shubnikov-Das oscillations, implying that the system is still in the quantum Hall regime when you are reducing the external magnetic field. For the system to be in the quantum Hall regime, actually you should have this equation preserved. The mobility times the total field should be larger than 1. The mobility in these samples are actually quite poor. It's a highly distorted system apparently, and so that implies that the total magnetic field should be larger than several Tesla. So now considering the fact that the total field could be coming from the applied field and a pseudo-magnetic field. Now, if the applied field is so small, then the pseudo-magnetic field should be larger than several Tesla. So this was another signature that there must be a pseudo-magnetic field present in the system, but the origin of that is more under investigation now. Now, what I told you so far is about chiral states. The moment that you actually bring the Fermi energy in between the Landau gaps, and you are addressing your chiral states that are ballistically propagating at the edge of the channel. And we know that the electrochemical potential that these states are creating at the local 4-terminal probes that we are having here is exactly the same. So the moment that you would measure the voltage difference, there is no voltage drop because there is exactly the same electrochemical potential built up at this electrode and the other one, and so you would measure 0 resistance. But if you're talking about induced magnetism, which means that you should have such picture with spin polarized situation of the Landau levels, at the Dirac point, you should be actually able to have both spin up and spin down electrons. One is electron-like and the other one is hole-like. And these states, because one is electron-like and the other one is hole-like, are going to counter-propagate in your channel, and that's why they are called helical states. The cool thing about helical states is that actually when you want to measure them, you have a different situation. For each edge state that gets to the contact, there are two available states present that it can scatter to. So either your electron can keep going on the red line, or it can scatter to the blue line and counter-propagate. So the presence of each electrode on the way of the current can actually create some form of spin mixing and spin scattering. And as a result, the electrochemical potential that is built up at each of the voltage probes that you're having is actually different, and that can create a voltage drop, and so there will be a non-zero resistance that you can measure. And as I mentioned, the presence of each voltage probe matters. So that means that when you're doing such measurements, geometry matters a lot. Depending on what kind of 2-terminal, 3-terminal, or 4-terminal geometries you would pick up, you will have different values for your helical states. And this actually gives you a tool to verify that you are indeed addressing the helical states. And now let's take a look back at our measurements. So this was the measurement that you saw earlier on. This is measured at 0 magnetic field. This is our Dirac curve. We see that there is quite some broadening at the Dirac curve, at the Dirac peak. And if I plot this in terms of conductance, I see that that plateau-like feature is actually a plateau at 2e²/h in conductance. And 2e²/h is actually counting for the two spin polarized edge states that are present at the Dirac point as a signature of the presence of spin polarized helical edge states in the system. And it's measured at 0 external magnetic field. Now, we evaluate this at various geometries. You see that you pick up different voltage probes. The conductance at different gate voltages is actually differing. But the moment that you're bringing the Fermi energy at the Dirac point, they're all merging at 2e²/h, which is a good signature for the fact that we are indeed addressing these spin polarized edge states. I'm also showing you another example of another sample with various 2-terminal, 3-terminal, 4-terminal geometries, and you see in all of them our conductance is actually reaching the value that it is supposed to reach based on the theoretical expectations. So now we are having the signature for the presence of quantum anomalous spin Hall effect, because this is actually measured without any external magnetic field. And now the question is that how would this plateau at 2e²/h is evolving versus external magnetic field? And this is what I'm showing you here. So we are starting with this 2e²/h because of the two edge states that are present there. But then as soon as we apply an external magnetic field, the system undergoes the spin flop transition, right? And that is creating spin mixing, and that's why the signal drops. But then increasing the field further is going to bring the magnetization again aligned with the external field. And so the signal goes up again. However, note that the external magnetic field can increase the Coulomb gap, the gap that you're having right here can increase, and that can also affect your detection of the helical states. But I am showing this because I noted earlier on that versus magnetic field, we are not having much of broadening in this system. And the reason for that could be because of the fact that already we have the spin polarized situation. So increasing the magnetic field does not much affect this broadening because the system is already spin polarized. So the effect of the external magnetic field can be small in comparison with the exchange-induced spin splitting. And last thing that I would like to highlight is the fact that this picture is also supported by our temperature-dependent studies. We actually see that at the Dirac point, by increasing the temperature, resistivity increases. This is a metallic behavior, and metallic behavior means that you have a gapless situation, which is well aligned with this schematics, because like there are always edge states present, so you have a gapless situation for your Landau levels. And lastly, we have realized that the first quantum Hall plateau at 2e²/h is persisting up to room temperature. This is a highly distorted system. Again, having a quantum Hall transport up to room temperature is quite surprising. So we are thinking that since we also saw anomalous Hall effect as a signature of the present magnetism up to room temperature, seems like that the persistence of the quantum Hall transport up to room temperature is assisted by the induced magnetism and spin orbit coupling, in accordance with the fact that theoretically it's expected to be like robust against disorder and temperature. So with this, I would like to actually summarize what the observations are in the magnetized graphene system. We realize that the magnetic graphene gets highly spin polarized and it can efficiently participate in the process of spin injection, not only electrically, but also thermally through the spin-dependent Seebeck effect. We could detect the spin-flop transition, observing that through the anomalous Hall effect, which actually showed that it's quite sizable. And it's also persisting up to room temperature as a signature of room temperature magnetism. We realized quite unconventional quantum Hall transport and possible presence of pseudomagnetic field in this heterostructure. And lastly, and most importantly, we have observed helical states at zero external magnetic field through the quantum anomalous spin Hall effect, telling us that without applying any external magnetic field, the induced magnetism and spin-orbit coupling would allow for the quantum coherent propagation of the spins at the edges of our graphene channel. And lastly, we realized that the quantum Hall transport is actually persisting up to room temperature for the first Landau level. And with this, I would like to acknowledge all people involved in this research. This research has been mainly done at University of Groningen and TU Delft back in the Netherlands, and also now in collaboration with Philip Kim at Harvard, and we have had theoretical supports from University of Regensburg, and also our materials have been coming from Columbia University and University in Valencia. And with that, I would like to thank you for your attention.